Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 23rd lecture, which I think will end the information about series. Last time we had given a definition about the product of two series. I want to write that definition on the board again, and we were looking at an example. Here was that definition. It says given series as k as n runs from 0 to infinity, a sub n, and the series is n running from 0 to infinity, b sub n, we put c sub n equal to the series as k runs from 0 to n of a sub k times b sub n minus k, where n is equal to 0, 1, 2, 3, forever, and call this the sum of the c sub n's as n runs from 0 to infinity, the product of the two series. Okay, so that's the definition that we had before. And as an example, we will produce or examine the product of the series, the sum if n goes from 0 to infinity of minus 1 to the n over the square root of n plus 1 with itself. Before I go any further, we last time showed that this series converged by the alternating series test. Okay? Okay. So here's what we know. Note that a sub n, when I'm trying to produce the product here, is equal to minus 1 to the n over the nth root of, square root of n plus 1, and b sub n, involved in the definition of the product of these guys, is equal to the same thing, minus 1 to the n over the n plus 1 square root. And so, c sub 0, let's write out some of the terms so we get familiar for how to find the product of this series. So c sub 0 is equal to the sum as k runs from 0 to 0 of a sub k, b to the n minus k, which here the n is 0 and the k is 0. It's just one term. It's a sub 0, b sub 0. Okay? And that's equal to, so when n is equal to 0 here, we're going to get 1 over the square root of 1 times 1 over the square root of 1, which equals just to 1. Okay. Now, c sub 1 is going to be equal to the sum as k runs from 0 to 1 of a sub k, b sub, here I shouldn't have said n, I should have just said 0 minus k. So here's 1 minus k. And here, this is going to be equal to a sub 0, b sub 1 plus, it's going to be a sub 1, b sub 0. And here, when we look at those terms, that's going to be 1, that's what this term is. And b sub 1 in this case is going to be minus, times a minus 1 over the square root of 2, plus, and well, these items are exactly the same, so I get the same thing. So it's a minus 1 over the square root of 2. And I'll rewrite that as minus the quantity 1 over the square root of 2 plus 1 over the square root of 2. Now C sub 2 is going to be equal to the sum as k runs from 0 to 2 of a sub k, b sub 2 minus k, which equals to, well, it'll be a sub 0, b sub 2, plus a sub 1, b sub 1, plus, it'll be a sub 2, b sub 0. A sub 0 we know to be equal to 1. B sub 2, so that's going to be 1 over the square root of 3, so it's 1 over the square root of 3. Plus, here, the a sub 1, b sub 1 are going to be the same, and so that's going to be minus 1 over the square root of 2 times minus 1 over the square root of 2. And then plus, this is going to be 1 times square root of 3 again. Okay. And so we're going to end up getting, of course, 1 times square root of 3 plus 1/4 plus, I'm sorry, 1 over the square root of 4, right? Plus 1 over the square root of 3 again. That's what I'll leave it. Let's look at one more term. So the C sub 3 will be equal to, well, it's going to be a sub 0, b sub 3, plus a sub 1, b sub 2, plus a sub 2, b sub 1, plus a sub 3, b sub 0. And then that's going to be equal to, well, it's going to be 1 times minus 1 over the square root of 4. Ladies and gentlemen, I think I might. Okay, that's fine. All right. That's what that is. And then plus minus 1 over the square root of 2 times 1 over the square root of 3 plus 1 over the square root of 3 times minus 1 over the square root of 2. And then plus a minus 1 over the square root of 4, which I'll rewrite as a minus the quantity 1 over the square root of 4 plus 1 over the square root of 2 times square root of 3 plus 1 over the square root of 3 times square root of 2 plus 1 over the square root of 4. And so here's what we can say. The product of this series with itself is, well, it's the sum of these C sub n's which would be equal to 1 minus it's just 1 over the square root of 2 plus 1 over the square root of 2. I think that was the first term. Let me check here. Yeah, that's right. And second term, I should say. And then plus, I'll rewrite this as 1 over the square root of 3 plus 1 over the square root of 2 times square root of 2. Or not square root of 4 there. 4 plus 1 over the square root of 3, and then minus what we just got, which is 1 over the square root of 4 plus 1 over the square root of 2 times the square root of 3 plus 1 over the square root of 2 times square root of 3, square root of 3 times square root of 2, however you want to write it, plus 1 over the square root of 4, and it keeps going, okay? And that's what we have. C sub n in general, it's going to be equal to the sum as k runs from 0 to n of this a sub k, b sub n minus k, as we said before, which is going to be equal to the sum as k runs from 0 to n. Well, the a sub k is nothing more than 1 to the k over the square root of k plus 1, and the times the b sub n sub n minus k. What that's going to be is going to be minus 1 to the n minus k over the square root of n minus k plus 1. And then we can simplify this a little bit. This is going to be equal to, well, we add the exponents here, and so it's minus 1 to the n. That doesn't depend on k, so I'm going to bring that out. So it's minus 1 to the n times the sum as k runs from 0 to n of 1 over, and I'll rewrite this as 1 square root. Well, no, I'll break it up. So I'll write down n minus k plus 1 times 1 over the square root of k plus 1. All right, so that's what we have. And let us note, this is something you can verify, it's an algebraic manipulation, that n minus k plus 1 times k plus 1, that's the same thing as n over 2 plus 1 to b squared minus n over 2 minus k to b squared. And that's definitely less than or equal to n over 2 plus k to b squared. I'm sorry, n over 2 plus 1 to b squared. Okay? So this is an algebraic, this part's an algebraic fact that you just square things. You get it. And of course, here I have something, and I'm taking away a positive thing, so that's less than just the original thing before I take away the positive. Then that gives us that 1 over n over 2 plus 1 to be squared is going to be less than or equal to 1 over this quantity, n minus k plus 1 times k plus 1. And so what that yields is that if I take the square root, both sides, I have 1 over n over 2 plus 1, square root, the square cancels, the square root, the square root. It's going to be less than or equal to 1 over n minus k plus 1, the square root of this, times k plus 1. Okay? We'll work with that just a little bit at the left-hand side. So what we have is, simplifying that left-hand side, this is 2 over n plus 2 is less than or equal to 1 over the square root of n minus k plus 1 times underneath the square root of k plus 1. Okay? And thus, what we have is that the absolute value of, or the norm of the C sub n's, the norms of the C sub n's, which is minus 1, the norm of minus 1 to n, sum, in this case it's absolute values, as k runs from 0 to n of 1 over the square root of n minus k plus 1 times k plus 1 is going to be equal to this is nothing more than the absolute value, because absolute value minus 1 to the n is just 1. As k runs from 0 to n of 1 over the square root of n minus k plus 1 times k plus 1. Now, Now, each one of these things are positive terms, so this is just equal to the sum as k goes from 0 to n of 1 over n minus k, square root of n minus k plus 1 times k plus 1. Okay, so now each one of those terms is positive, and that's going to be greater than the sum as of 2 over n plus 2. Okay? And that's as k runs from 0 to n. Now this sum is a sum of quantity that doesn't depend on k. So this is a constant, and sum of a constant, well, really we're summing it up n plus 1 time. So this is equal to 2 over n plus 2, what we're summing up, times n plus 1. Okay? Now, if you know that the limit as n goes to infinity of 2 times n plus 1 over n plus 2, that's going to be equal to 2, if you use L'Hopital rule to get it, then that means that the norm of the c sub n's, that the limit of them, as n goes to infinity, they have to be bigger than, even if it's converted, got to be bigger than that 2, so it cannot be equal to 0. Okay? And so what that says then is that the limit as n goes to infinity of the c sub n's can't be 0. And remember, those c sub n's are what we're summing up to get the product of the two series. And thus, what we're finding is that the series of the c sub n's, as n runs from 0 to infinity, diverges, and it's diverged by the divergence test. Okay, so let me write up this comment of what this example showed. So this example shows, this was an example of a product of two converging product of a product of, I'll write it this way, of two series where the product diverges even though each series converge. So that's interesting. Okay, so we'd like to have some kind of information that will help guarantee when the product will converge, because it doesn't seem like even if the two series, well, we have an example here where the two series did not, the two series did converge, but the product didn't. So what do we need to ensure that the product will converge? Well, here's the theorem. It says, suppose, several things. First thing is that the series as n runs from 0 to infinity of a sub n converges absolutely. Part B, we're going to have the notation that the series as n goes from 0 to infinity of a sub n equals to a. Look, if that series converges, then absolutely, then it converges as is, and so we're going to call it when it converges to A. We're going to say that the sum as n runs from 0 to infinity of b sub n equals to big B, and the c sub n equals to the sum as k, this is the fourth thing we're assuming, letting happen. K run from 0 to n, it's going to be of a sub k, b sub n minus k. So this is the product. Well, it's the terms involved in the product. And this is true for n equal to 0, 1, 2, forever. Then, this series, as n goes from 0 to infinity, c sub n, so the product, that's going to equal to a times b. Okay, we'd like to prove that. This proof is going to involve a lot of symbolic representation to try to simplify things, but here's what we have. We're going to left a sub n be equal to the sum as k runs from 0 to n of a sub k. So the big a sub n's are the partial sums. B sub n is going to be equal to the sum as k runs from 0 to n of the little b sub k. So that's the nth partial sum for the little b sub k's. And then we're going to have, I'm going to call it script c is sub n is going to be equal to the sum as k runs from 0 to n of the c sub k. So that's the partial sums for the product. And we're going to have this beta sub n, okay, is going to be equal to b sub n minus b. So that's the notation we're going to have. Okay, well, then the script c sub n, well, what's that going to be? That's going to be the c sub 0, the little c sub 0, plus c sub 1, plus c sub 2, all the way up to c sub k. That's what it's going to be. And what's that going to be equal to? That's going to be equal to, the first guy is a sub 0, b sub 0, plus the next guy, c sub 1, is a sub 0, b sub 1, plus a sub 1, b sub 0. The next guy is a sub 0, b sub 2 plus a sub 1, b sub 1 plus a sub 2, b sub 0 plus, excuse me, we keep going until we get down to the last term, the k term. And that's going to be a sub 0, no, I guess I'm calling it the nth term, okay? This should have been the nth. I made a mistake there. A sub 0, b sub n, plus a sub 1, b sub n minus 1, plus a sub 2, b sub n minus 2, plus we keep going all the way up to the last one will be a sub n, b sub 0. Okay, now that is going to be equal to, so all those terms added together. Okay, look, you got a sub naught times b sub naught, a sub naught times b sub 1, a sub naught times b sub 2, and if you just look at the a sub naught times things and factor them out, what they're involved with this sum, you have a sub naught and then the b sub 0 plus b sub 1 plus b sub 2 all the way up to b sub n. Well, that sum is big B sub n. Big B sub n, I should make a little n. Okay. Plus this would be a sub 1, b sub n minus 1. We can continue like this. Plus a sub 2, b sub n minus 2. All the way up to a sub n, okay, a sub n, b sub 0. That's what we'll That's going to be equal to a sub 0 with the big B sub n to be written down as big B minus the beta sub n plus a sub 1 big B minus beta sub n minus 1 plus a sub 2 big B plus beta sub n minus 2 plus all the way up to a sub n, b plus beta sub naught. Okay, that's what we got. Okay, and then that is going to be equal to a sub n. We'll multiply all this out. Factor out b. So it's a sub n b plus a sub naught beta sub n plus a sub 1 beta sub n minus 1 plus a sub 2, put that term in, a sub 2 beta sub n minus 2 all the way up to a sub n beta sub 0. That's what we got. Now, for notation's sake, here we're going to let gamma sub n be equal to a sub 0 beta sub n plus a sub 1 beta sub n minus 1 plus a sub 2 beta sub n minus 2 all the way up to a sub n beta sub 0. So this part. Okay. Remember, this is what c sub n is equal to. And what are we trying to show? That the script c sub n's, which were the partial sums for the product, we're trying to show that that converges to a to b. Okay? Let me write that down. We wish to show that the limit as n goes to infinity of the script c sub n's equals to a times b. Well, since the limit as n goes to infinity of the a sub n times b. Okay, now look, a sub n's were the partial sums for the series of the little a's. And so we know that that partial sums converge to a. So this part of the script c sub n, it goes to ab. So the rest of it, which we call gamma sub n, needs to go to 0. So thus, we only need to show that the limit as n goes to infinity of the gamma sub n equals to 0. So that's my goal. Okay. Well, in terms of a little bit more notation, we're going to put alpha equal to the answer. Alpha equal to the series is n runs from 0 to infinity of the absolute values of the a sub n's, which we know exists. It exists. Okay, we know this exists as a number. So I know it exists as a number. That's what I'm writing. How do I know that this exists as a number? Well, we're assuming that the a sub n's, that sum, was absolutely convergent. So that's why we have this. Okay. Now, we'll let epsilon be greater than 0 be given. Okay. Since the limit as n goes to infinity of the b, and not beta, but b sub n equals to b, converts. Then the limit as n goes to infinity of the beta sub n's, that's got to be equal to 0. And that had to do with the definition of the beta sub n's. Okay? Okay. All right. Hence, we can choose a natural number and we call it n such that the norm of the beta sub n will be less than epsilon. I'm going to say less than or equal to epsilon. And that's true for all n greater than or equal to n. Now, for all n bigger than or equal to this big N, let's look at that gamma sub n inside norms. Well, let's just look at it without norms first. Okay, here's what I want to do. I want to rewrite this gamma sub n. Okay, it was a sub naught, b sub n plus a sub 1, b sub n minus 1, plus, we're going to keep going, we'll get up to a sub little n minus big N minus 1, and then this will be b, these are, no, these are betas, okay? All right, these are betas. Betas of n plus 1 here, plus, I got some more, so I'm going to write some more terms down here. It would be a sub n minus big N, that's a little n first, big N after, beta sub n plus a sub little n minus big N plus 1, and then beta sub big N minus 1, and we keep going all the way up to the last term, which is a sub n beta sub 0. That's what we have. Well, that's a long form of what gamma is. So, for n bigger than or equal to big N, we have that this norm of gamma sub n will be less than or equal to, and so I'm going to split it up, gamma sub n, into two parts and take the absolute value of each part the norm of each part, and that's involving the triangle inequality to get this less than or equal to. So it's alpha sub 0, b sub n plus alpha sub 1, not b, beta sub n minus 1 plus all the way up to a sub little n minus big N minus 1, beta sub big N plus 1, and then plus the absolute value of the second part, which is a sub n minus n beta, and this will just be n plus the big N. A sub n minus n plus 1, and then this would be beta of n minus 1 plus all the way up to the last term, which was a sub n beta sub 0. That's what we have. Which is less than or equal to. Well, for this particular one, I'm going to say, well, that sum, the norm of the sum is less than or equal to the norm of each part, okay? And then each part is a product. And so I'm going to say this is less than or equal to the norm of a sub 0 times the norm of beta sub n plus the norm of a sub 1 times the norm of beta sub n minus 1 plus all the way up to the norm of a sub little n minus big N minus 1 times the norm of beta sub big N plus 1 plus this guy I'm just going to write down as is. Okay, so this is a sub little n minus big N beta sub big N plus a sub little n minus big N plus 1 beta sub n minus 1 plus all the way up to a sub n beta sub 0. All right, now this is going to be less than or equal to. Now, these beta sub n's are bigger than n. And every one of these indexes for the betas are bigger than n. And so that's going to be able to be replaced by something bigger, which is epsilon. So this is going to be a sub 0's norm times epsilon plus a sub 1's norm times epsilon all the way up to the norm of a sub n minus big N minus 1 times epsilon plus, and this quantity, which I'm going to write here to the side. So it's a sub little n minus big N, beta sub big N, plus a sub little n minus big N plus 1, beta sub big N minus 1, all the way up to a sub n beta sub 0. Now, this guy, you can pull out the epsilon and say, well, that's times the sum as k runs from 0 to n minus big N minus 1. I think that's the last one. Yep. Of absolute, or the norms of a sub k's, and then plus this guy here, which I'll write down a sub n minus big N, beta sub big N plus dot 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 all the way up to a sub n beta sub naught. Okay, this is going to be less than or equal to epsilon times alpha. What was alpha? Alpha was the sum of the, it was equal to the series of the absolute values of the a sub n's. And so that's just part of them. So this, replacing it by more, remember that's going to be positive, replacing it by something more, it's going to be less than or equal to. And then plus, there's this absolute value of a sub n minus n, b sub n, same thing we had, plus a sub little n minus big N, plus 1, beta sub big N, minus 1, plus all the way up to a sub n, beta sub 0. Okay. Now keeping n fixed, big N fixed, and letting n go to infinity, little n go to infinity, we have the lim sup is n goes to infinity of the norm of gamma sub n. Remember, that's the guy we want to show goes to 0. Is less than the lim sup, less than or equal to the lim sup as n goes to infinity of the epsilon times alpha plus this quantity right here, the a sub n minus big N beta sub big N plus a sub little n minus big N plus 1 beta sub big N minus 1 all the way up to adding a sub n b sub beta sub 0. The lim sup of all this guy, which is less than or equal to the lim sup as n goes to infinity of epsilon times alpha, just that part, plus the lim sup of every one of these. And I'm going to make this guy bigger by taking the absolute value of these, the norms of each individual one, using triangle inequality, and then splitting up those norms into the product of individual norms. So here I'll write down lim sup of a sub n minus big N times the norm of beta sub n. Okay. Plus norm of a sub n minus big N plus 1 beta sub big N minus 1. Both of these guys are norms. And then plus all the way up to the norm of a sub n times the norm of beta sub 0. Okay. Now, that goes to 0. So we end up getting epsilon times alpha plus 0 as the limit as k goes to infinity of the norm of a sub k's must equal to 0 because the sum of the a sub k's converge. And so by the divergence test, this has got to go to 0, otherwise it couldn't converge. Thus, we have 0 is less than or equal to the lim sup as n goes to infinity of the gamma sub n's inside norms, which is less than or equal to epsilon times this alpha. And so since since epsilon is arbitrary, okay, then that tells us that the lim sup as n goes to infinity. Remember, I asked this, gamma sub n, okay, equals to 0. And so what that tells us is that the limit as n goes to infinity of gamma sub n equals to 0. And thus, the limit as n goes to infinity of gamma sub n equals to 0. That's what we want to prove. So that ends that theorem. Next, I'm going to write down the theorem without proof. So here's the statement. It says if the series sum of the a sub n's, sums of the b sub n's, and the sums of the c sub n's converge to big A, big B, and big C, respectively. Okay? And C sub n is equal to A sub 0 B sub n plus A sub 1 B sub n minus 1 plus, that's the terms involved in the product. And the last one's going to be A sub n B sub 0. Then, conclusion of this theory is that C has got to be equal to A times B. So this theorem that I just written on the board had that the two series involved, they converged, and the product is known to converge. Then what the product had to converge to was the multiplication of what each of the individual series converged to. In the first example we did, the two series involved, the same series, they both converged, but we didn't have that the product converged. Okay? So that's how this theory didn't apply to this situation. I'm not going to prove that. Instead, we're going to move on to a definition. And we're going to say let K sub n as n equaling 1, 2, 3, forever, be a sequence in which every positive integer appears once and only once what that means is that is the K sub n is a one-to-one function from a set of natural numbers onto a set of natural numbers. So we let, for notation, say A sub n prime equal to A sub k sub n. And that's true for n equaling 1, 2, forever. Then the series of A sub prime n running from 1 to infinity, is called a rearrangement of the series of just the A sub n's. So we're rewriting the order of the terms of the A sub n's. You know, in finite additions, the order that we write things doesn't matter. But this is infinite. Does it matter or not? That's what we're curious about. Okay? Let's quickly look at just an example. And then we'll call it quits. Very quick example. His sum as n runs from 1 to infinity of minus 1 to the n plus 1 over n, which equals to 1 minus 1 half plus 1 third, minus 1 fourth, plus 1 fifth, minus 1 sixth, plus 1 seventh, and so forth, is a convergent alternating series. Okay. a rearrangement of this series is 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6 plus 1/13 plus 1/15 minus 1/8, and continue on in this fashion, in which two positive terms are followed by negative. We're going to look at this rearrangement and look at the original series and compare about if they converge to the same thing or not. That's enough for tonight. Thank you very much.